Hello everyone, welcome to my channel. This is the first of a series of lessons I'm going to present on distribution theory, which is a branch of statistics. And I'll kick off this first lesson by looking at joint density functions, also known as joint probability density functions. Now we have an example here. The focus or emphasis is on random variables capital X and capital Y, which can take on values small letter x and small letter y respectively. So we have an example here, but I want to talk about defining characteristics of our joint density function or joint probability density function of random variables capital X and capital Y. Three defining conditions. The first defining condition is that the joint probability density function, or simply joint density function, of random variables capital X, capital Y, which can take on values small letter x and small letter y respectively, must be non-negative, must be positive. Of course, you don't expect probabilities to be negative. Number two, total probabilities of x and y should be equal to 1. In other words, the double integral from minus infinity to positive infinity of our joint density function of capital X and capital Y, which can take on values small letter x and small letter y respectively, like I said, must be equal to 1. That double integral must be equal to 1. The third condition is that our random variables capital X and capital Y, which can take on values small letter x and small letter y, are continuous. So these are the three defining conditions that we need to know. Of course, we are going to look at many other conditions as we proceed, but these are the three major conditions of any probability density function. It must be non-negative. In other words, it must be 0 or positive. The double integral must be equal to 1. And the random variables x and y, which can take on values small letter x and small letter y, must be continuous. Right, so let's look at this example we have here. So we have example 1. Of course, example 2 is going to come in my next lesson. So example 1, consider the following joint density function, or joint probability density function, as you would want to call it. We have f of x comma y is given by k 2x plus y in brackets multiplied by k there, for x ranging from 0 up to 1 and y also ranging from 0 up to 1, and also that this function is equal to 0 everywhere else or elsewhere. Now, the first one is question 1.1. We're required to determine the value of k. Now, we're going to use this condition here. We're going to use this condition. For any probability density function, total probability must be equal to 1. The double integral in this case, because we're dealing with two variables, the double integral must be equal to 1. So we are going to have to integrate this from minus infinity to positive infinity for x, and from minus infinity to positive infinity for y, and we're going to equate to 1. That will give us the value of k. So let's start with that one. 1.1. So this is, I'm going to call this page 3. We have page 2 there, because question 1.2 continues, as you can see here. 1.1 continues with C on page 2, and also 1.2 is on page 2. So let's look at the first one. We're required to work out the value of k. Like I said, we're going to use this condition here. This condition here. The double integral of our joint probability density function should be equal to 1. So as follows. So 1.1, and we're saying a, the double integral from minus infinity to positive infinity, by definition, basically, to positive infinity of our function. And notice we're talking about this function here, k. Let me just write down the formula first. So we're talking about f of x. These are capital X and capital Y, like I said, which can take on values small letter x and small letter y respectively, dx dy is equal to 1. Now let's put in that expression because we do have it. So what we're saying now is, and our limits of integration, remember, from 0 up to 1, and then from 0 up to 1 for y as well, and 0 elsewhere. So I'm just going to focus on these values as our limits of integration. So we're changing now. The outer one is for y because y is outside there. The inner one is for x. So we're saying from 0 up to 1, and then from 0 up to 1 of this part here is going to be k, 2x plus y, and then we have, remember, dx dy. This must be equal to 1. So we have to solve that equation there. Now let's proceed. So we're going to, like I said, going to focus on this part first. Keep dy out as follows. I like to answer this as follows by using a square bracket there to show you that we are working on the inner integral first from 0 up to 1 of k 2x plus y, and I'm going to say dx. We have dy dx here. We have dy outside, and this should be equal to 1. Now let's work on this one. Well, there are many ways in which you can deal with this. I'm going to try to be as fast as I can, but not leaving out some information. So as follows: 0 up to 1, the first one, and we're saying the inner part. Now remember, k is a constant. So I'm going to take k out, and I'm going to distribute the integral and dx as follows. So k out, and let me open another bracket here. And then I'm saying the integral from 0 up to 1 of 2x, and I'm going to have to say dx, and then I have a plus sign there. The integral from 0 up to 1 of y dx, and I'm going to close this bracket here, that one, and I'm going to close the other bracket, closing this one here, and I'm going to say dy. This should be equal to 1. Now let's work on the two integrals inside there. So this part here is fine. That one is very simple and straightforward, taking us to page 4. Let me just move this one down a little bit. Page 4. So you're able to see, right? Page 4. So now I'm saying what we have there implies the integral from 0 up to 1, and I'm going to keep that bracket, k, and I'm going to keep that bracket. This part here, the integral of 2x, basically, remember 2 is a constant, so you can say 2, but x, it will be, remember there's a power of 1, so I'm going to add 1 using power rule, and I'm going to divide. Remember, our limits of integration will be from 0 up to 1. So I'm done with the first part. Now I'm coming to the second part. Remember, y is a constant when I'm integrating with respect to x. So y can come out. So I'm going to have y, the integral from 0 up to 1 of 1, basically, and then I have dx. And I have to close that and say dy, and I say this is equal to 1. Now let's work on this and that part. So this implies the integral from 0 up to 1. I'm going to keep k out, and I'm going to, you can see these twos cancel. So I have x squared, limits of integration from 1 up to, from 0 up to 1. Let me close that bracket, and then I'm going to, don't forget that this k here is supposed to cover that part and that part. So this k, look at these two brackets here. K takes care of the entire inner part. So I'm going to have to be careful here. Let me put another bracket, and then I'm going to say plus y, the integral of 1 with respect to x is basically x, and I'm going to use a round bracket there, and I'm going to say limits of integration from 0 up to 1. Let me close it like this, and so now I have to close this bracket. I close it like this. That k takes care of everybody inside, and I can close again. That closes this bracket here. So I'm going to say dy is equal to 1. I know there are too many brackets, but yeah, let's work on this one. So what are we saying? One step at a time. Integral from 0 up to 1. Keep k out. Let me keep this bracket. Now this part here, remember, it's going to be 1 squared minus 0 squared. I'm done with these two brackets. Then I'm going to have to say plus. I have y there, and I can keep this round bracket, put 1 and put 0 there to be 1 minus 0, and I close. These brackets are done, and I have to close this. That takes care of that bracket there, and I have k, so I can also close the second one there that closes this bracket, and then I'm going to say dy, and I'm going to say this is equal to 1. Now let me simplify what is inside there. So we have the integral from 0 up to 1. What do we have now? What we have now is k. Let me keep that bracket out, and inside there now, if you allow me to keep that bracket, this is 1 basically plus y. You can see there, and then I'm going to have to close this bracket here, close again, dy. This is equal to 1. Now at this point I can easily take the k out because it's a constant, and then I'm going to distribute the integral and dy. So what I have now is k times the integral from 0 up to 1 of 1 dy plus the integral from 0 up to 1 of y dy. This must be equal to 1. Notice I'm closing that bracket there. So this taking us to, let me just squeeze in here. We're saying k, the integral of 1 with respect to y is actually y. So I'm saying y, we're talking about limits of integration of 0 up to 1. And then I'm going to say plus the integral of y. Remember, there's a power of 1. You add 1 and then divide. So y squared over 2, the integral, limits of integration from 0 up to 1. I'm going to close that bracket, and I'm going to say this equals 1. So all I have to do is simplify what I have inside there. Taking us to page 5. So what do we have now? What we have is the following. Let me move this one down a little bit. What we have now is the following. So we're saying that is equal, implies k. Inside there now, we have y minus limit of integration 0 and 1. So I'm going to have to substitute. Let me get rid of this one here. I don't want to carry on with the y there. Basically, I'm saying you have 1 minus 0. That takes care of that part. And then this part here, we're going to say plus. Remember, 1 squared over 2 minus 0 squared over 2. That's what this means. And what are we saying? We're closing this and we're equating this to 1. Now, let's simplify what we have inside brackets there. K, we have 1 here, and that part is going to be half. And we're saying this is equal to 1. Remember, this is 0. 0 squared is 0 over 2, 0. 1 squared is 1 over 2, half. And there, 1 minus 0 is 1. And what is 1 plus half? The answer is 3 over 2. So k, of course, you can see that that's 2 over 2 plus 1 over 2. This is equal to 1. And that part there is exactly, denominators are the same. You can actually keep the denominator and then add 2 plus 1. Sorry, 2 plus 1. My hand is going ahead of me. So that's 2 plus 1. I'm going to rewrite that 2 plus 1 equals 1. What are we saying? This is k, 3 over 2 equals 1. Divide by 3 over 2 both sides. What are we saying? We're saying k, 3 over 2 over 3 over 2 equals 1 over 3 over 2. So k will be equal to 2 over 3 if you work it out on the other side there. This is the final solution to the value of k. But remember, this one here, I said that must be a 2. So I'm going to have to fix that one before I move on. I may end up forgetting. So that must be a 2. Yeah, it's not dried yet, but let me just, yeah, that should be fine. I think you can see that. So that's how you answer this question here. A little bit tricky in terms of handling the double integral, but with practice, you should be fine. All right, let's move on to the next question. So now that we know the value of k, so we can actually, when we move to the next step, which is determining what we call marginal density functions, we have marginal density function of x and marginal density function of y. Determining these, we have to rewrite our function, of course, with k as 2/3, as you've seen. So number B, number 1.1b, and I'm actually now on page, let me just check here. Page 5 was the last one. This is page 6. page 6, and B, marginal density function of random variable capital X, which is also written as f of small letter x, but we write capital X as a subscript to show that the random variable is capital X, which can take on a value of small letter x. So the formula says, please take note of this. The formula says f of small letter x, of course, respecting our random variable x, would just be the integral, right? By definition, from minus infinity to positive infinity of our joint probability density function, which is this one here. These are capital X and capital Y, which can take on values small letter x and small letter y. Remember, this is a function of x, so we have to integrate with respect to y. You are looking for the marginal density function of capital X, we have to integrate with respect to small letter y. So let's substitute what we know. This is minus infinity. Let's substitute what we know. So we're saying this is equal to remember, limits of integration. This is just by definition for minus infinity to positive infinity, but we know that it's 0 elsewhere, but it's defined for x ranging from 0 up to 1 and y ranging from 0 up to 1. So therefore, the limits of integration with respect to y must be from 0 up to 1. So we're saying from 0 up to 1. What are we dealing with? We're dealing with 2/3 of, remember now, we're taking k as 2/3 because we've worked that one out. And we must put that expression and then our limits of integration 0 up to 1, as you can see here. So 2x plus y, what are we integrating with respect to? With respect to y. Of course, the y will go, and you're going to remain with an expression in terms of x, which agrees with what we have there. So let's take 2/3 out. It's a constant. The integral from 0 up to 1 of 2x plus y with respect to y. What I'm going to do, I'm going to distribute the integral and dy, keep 2/3 out, 2/3, and I'm going to use brackets now. And I'm going to say the integral from 0 up to 1 of 2x dy plus the integral from 0 up to 1 of y dy, like so. Now notice that we're integrating with respect to y. So 2x is a constant. We can take it out. So this is 2/3 multiplied by 2x, the integral from 0 up to 1 of 1, if you like, dy. Of course, 2x times 1 is 2x. So this is just fine. And then here, it's just okay. We can actually do the power rule here, use power rule. The power is 1 there. We're going to have to add 1 and then divide. So this is y squared over 2, and the limits of integration from 0 up to 1, like so. Now, let's work on this one. So what we have now is keep 2/3 out, 2/3, and what we're saying is 2x, the integral of 1 with respect to y is basically y, and limits of integration, we're talking about from 0 up to 1, right? This part is done. And then that part, I can also keep half out, and then I'm going to say substitute 1 into y squared, it will be 1 squared, substitute 0, it will be 0 squared, like so. And then I close that bracket. Right, finally, maybe next step, 2/3, what are we saying here? 2x, and then inside these brackets here, we're going to have 1 minus 0. Remember, you substitute 1 and substitute 0 as well. And then coming this side, what do we have? We have half of, in brackets there, we just have 1. Because 1 squared is 1, minus 0 is 1. We also have 1 here. So let's just clean up, and we are at the end of the first part. Page 7. So now we are saying basically that if we clean up that expression, it gives us 2/3. Inside there, we have 2x times 1 is 2x plus half. Basically, that's what we have. Expand that. What do we get? We get 4x over 3 plus, multiply this by that. Remember, you're going to have 1/3 because the 2's cancel. You have 1/3. Let's factorize. Take 1/3 out. 1/3. And what do you have in brackets now? It's 4x plus 1. This is our final solution. And remember, now we are saying f of x, remember marginal density function of x, which can take on random variable capital X can take on a small letter value x, must be equal to 1 over 3, and then we have 4x plus 1, and of course this is defined for x is ranging from 1 all the way up to 0, or from 0 up to 1. So this is the marginal density function of x, random variable x. Let's look at the marginal density function of the random variable y, which is our part C of question 1, point 1, part C of question 1.1. The marginal density function of capital random variable capital Y, written like this, which can take on, of course, we know that that square, that capital Y can take on value small letter y. All right, I'm gonna bring up maybe 1 or 2 examples that deal with real life problems that one would actually use to explain what we call the joint probability density function. So you can understand what kind of quantities do the random variables capital X and capital Y take. It could be time, it could be just probability in terms of percentages and so on. Let's look at the number C. Like I said, the marginal density function of random variable capital Y. So number C, 1.1 C, so we're saying the marginal density function of random variable capital Y is going to be equal to, by definition, the integral from minus infinity to positive infinity of our joint random variable, a joint probability density function of random variable x and y, which can take on values small letter x and small letter y respectively. But remember, now it has to be a function of y, so we integrate with respect to x. That's what it is by definition. But we understand the limits of integration for x are actually from 0 up to 1 as well. You can see here from 0 up to 1. So this integral then changes to the integral from 0 up to 1 of this expression here. We know what it is. It's this one here with k as 2/3, as you saw in part A of 1.1. So we're going to say 2/3 of 2x plus y, and we're integrating with respect to x, so that x can go and we remain with y, which agrees with what we have there here. Now take 2/3 out, it's a constant, times the integral from 0 up to 1 of 2x plus y, and we're integrating this with respect to x. I'm going to distribute this and that, keep 2/3 out, 2 over 3, and allow me to use square brackets now, times the integral from 0 up to 1 of 2x with respect to x, plus the integral from 0 up to 1 of y with respect to x, like so. Now, y is a constant, I can take it out like I did in a previous case. So keep 2/3 out, 2 over 3, and here, remember the trick is power rule. It's 2 times x power 2 over 2. Remember the power 1 here, you add 1. 1 plus 1 is 2, and then you must divide. You can see these cancel, but limits of integration are from 0 up to 1. I'm done with the first part, that part. Now I'm going to say plus. Y is a constant, you can take y out, times the integral from 0 up to 1 of 1 dx. So where is 1 coming from? Well, 1 times y is y. So when you take y out, there's 1 that remains inside there. Right. Let's simplify this, and then we're almost done. Continuing, so we have 2/3 outside, and what do we have there? So we now have 1 squared minus 0 squared, because remember there's only x squared here. Substitute 1, substitute 0, and then plus y, and this is going to be x. Limits of integration from 0 up to 1, and then we can close that. Going to the next page, finishing this off, we're now basically saying almost done. This is this was page 7. This is now page 8. Now we're saying that answer simplifies to 2 over 3. Inside brackets there you have 1 plus, if you put the expression there, put the numbers 1 and 0, you have y 1 minus 0, like that. This is 2 over 3. What are we saying? 1 plus y, basically. And there's no need to expand this because the expression inside there is just fine, linear, just fine. So we can say, therefore, the marginal density function or marginal probability density function of random variable y, which can take on the value small eta y, is equal to 2 over 3, and then we have 1 plus y, like so. What else do we know? We know that this is defined for y ranging from 0 up to 1. There is your story. This is how you work out what we call marginal probability density functions, or sometimes just known as marginal density functions of x and y. Now we have the last question here, just to finish this off. The last question here says, prove that x and y, random variables capital X and capital Y, are not independent. So there's another fact here that I'm gonna show you. 1.2, allow me to use another page here for 1.2, page 9. 1.2, condition for independence is that for independence, this is the condition we must have. The joint probability density function for our random variables capital X and capital Y, which can take on values small letter x and small letter y respectively, this one here must be equal to the product of marginal density functions of x and y. This is the condition. So all we have to do now is multiply the two functions that we already obtained and see if we get the original joint probability density function. If that is not the case, then there's no independence, and therefore we are able to show that the two random variables x and y are not independent, and therefore we can say that they are dependent. So we have the two functions. So first, left hand side, remember, proof, left hand side, it's this part here. We know this is equal to this part here with 2/3 there, is equal to 2 over 3 of 2x plus y. Of course, we know the conditions. The conditions are these two and 0 elsewhere. But let's just keep it this way. That's our left hand side. What about right hand side? Right hand side is equal to that part there. Let me just capture it here. We know from there is our marginal density function for x. Where is it? Let me check the actual page. I have one for y here, and for x there it is. So this is the marginal density function for x. So we're going to say 1 over 3 times 4x plus 1, and then multiply by the marginal density function for y is this one here. This one here. I'm going to say times 2 over 3, and then I'm going to have 1 plus y. Simplifying this, you'll agree with me that the answer is 2 over 9, and we have 4x plus 1 multiplied by 1 plus y. Looking at this expression and that expression, they are not the same. So we can say, therefore, left hand side is not equal to right hand side. Therefore, x and y are not independent. This is how you show this. Simple and straightforward, but yeah, after obtaining these two, it's very straightforward to show, because you simply multiply them and see if the answer turns out to be the joint probability density function. If it's not, no independence. If they are the same, then you can conclude that the random variables x and y are in fact independent. Right, I'm going to stop here in this video. See you in the next one.